Namaste, everyone. Welcome. Prepare to look at your world in a completely different way today. We're diving straight into this explainer to decode the unseen chemical drama happening all around us, literally every single day. We often picture chemistry as just lab coats and safety goggles, right? But the reality, you are witnessing incredibly complex chemical reactions in your own kitchen, out in the backyard, and even right inside your own body.
So, आज हम क्या डिस्कवर करने वाले हैं? Think of this as the ultimate movie trailer for the unseen world. Here is our roadmap for decoding the chemistry of our world. We'll start with everyday chemical mysteries, move on to the language of chemistry, look at types of chemical reactions, get into the displacement drama, and finally, oxidation, reduction, and you. Let's get right into it.
Part 1. Everyday Chemical Mysteries. Spotting the Unseen Changes. Let's see what kind of chemical magic is hiding in plain sight. To really get this, we've got to understand the difference between a simple physical change and a true chemical change. Like if you take an ice cube and melt it, sure, it looks different, but its fundamental identity hasn't changed at all. It was water, and it's still water. That's just a physical change. But kya hota hai jab you leave a glass of milk out on the kitchen counter on a blistering hot summer day? Well, the milk spoils, it smells awful, it gets all clumpy, the taste is ruined. Or think about the food you just had for lunch getting digested right now. In these situations, the nature and the actual identity of the initial substance completely transform into something brand new. That is a chemical change.
But that brings up a really crucial question for our everyday detectives. If we don't have some high-powered microscope to literally watch the atoms rearranging themselves, what tells us a chemical change has actually happened right in front of our eyes?
Okay, let's dive into this because nature actually gives us 4 very specific, undeniable clues. First, if you mix substances together and see a sudden physical change in state, like a solid instantly forming out of 2 clear liquids, boom, you've got a chemical reaction. Second, a rapid change in color is another massive clue. Third, if bubbles suddenly start fizzing up and popping out of nowhere, that's the evolution of a gas. And finally, if the container suddenly gets super hot or drops to be ice cold to the touch, that drastic change in temperature means you can be absolutely sure a chemical reaction just went down. Section 2, the language of chemistry, writing the script. Let's look at how we actually translate these actions onto paper. Imagine having to write out when a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide every single time you want to talk about that experiment. Honestly, that's just a long, exhausting sentence, right? So how do we translate that wordy description into a concise universal chemical code? Let's move to the board and see how this builds step by step. First, we simplify the whole sentence into a word equation. We literally just write magnesium plus oxygen, draw an arrow to show the change, and write magnesium oxide. It's better for sure, but we can go even faster. Step 2 is the skeletal equation. This is where we use chemical symbols. Mg plus O2 yields MgO. But wait, hold on, we have a problem here. There are 2 oxygen atoms on the left, but only 1 on the right. And in chemistry, matter absolutely cannot just disappear into thin air. So we arrive at step 3, the balanced equation. By putting a 2 in front of magnesium and a 2 in front of magnesium oxide, we make sure the number of atoms for every element is exactly the same on both sides. Balancing equations is absolutely essential, guys, because it proves that the universe keeps a perfect, meticulous accounting of every single atom. Moving on to part 3, types of chemical reactions. Let's explore the different genres of our chemical drama. So elements, just like characters in a movie, they form relationships, they swap partners, and yes, sometimes they even break up. Think about a single complex compound deciding it just can't stay together anymore. What actually happens when these molecular elements decide to break up into simpler, smaller pieces? Well, we call this a decomposition reaction. But here's the thing. Molecules don't just break up for no reason. They need a push. They require energy to make that split happen. This could be thermal energy from intense heat. It could be electrical energy from a battery, like when we literally zap water to chemically split it into hydrogen and oxygen gas. Or, and this is super fascinating, it can be light energy from the sun. If you expose silver bromide to sunlight, the light energy actually breaks it down into silver and bromine gas. Actually, scratch that. It doesn't just break it down. This specific light-triggered breakup is the exact chemical magic that made old-school black and white photography possible. How cool is that? All right, section 4, the displacement drama, stealing the spotlight. This is where the real backstabbing happens. Okay, picture this. Imagine a highly reactive, very strong element walking into a room and seeing a weaker, much less reactive element happily partnered up in a compound. What happens when this strong metal meets the weak metal's compound? Well, it steals the spotlight and it absolutely steals the partner.
Now, what's really interesting about this slide is the visual proof of this exact drama. Just look at this simple iron nail suspended in that beautiful blue solution of copper sulfate. Iron is a much stronger, far more reactive metal than copper, so the iron literally kicks the copper right out of the solution. Over time, you'll see that blue solution fade to a pale green as it turns into iron sulfate, and the kicked out copper, it forms this rusty brown coating all over the nail. It is literally a hostile takeover, happening right inside a test tube.
Sometimes, though, the drama is a little more mutual. Enter the double displacement reaction. This is a reaction where two completely different compounds decide to mutually exchange their ions. They're effectively swapping partners. And very often, this brand new pairing creates an insoluble salt that just drops right out of the liquid as a solid powder. We call that solid a precipitate. It's kind of like two couples going to a dance, deciding to swap partners, and then one of the new pairs immediately sits down and refuses to dance anymore.
And that brings us to our final act, Section 5, Oxidation, Reduction, and U. The invisible war.
So there is this war happening constantly all around us, and it's driven largely by an element we literally cannot live without: oxygen. Oxygen is incredibly greedy, you guys. It loves to interfere with other elements. So we really have to ask what chemically happens when substances gain oxygen from their environment, or on the flip side, when they lose it. We define this using two specific terms. Oxidation is when a substance gains oxygen or loses hydrogen during a reaction. Reduction is the exact opposite, losing oxygen or gaining hydrogen. Now, here's the catch. These two almost always happen together. If one substance is out there gaining oxygen, another substance has to be losing it. We call this a redox reaction. It's like this constant cosmic balancing act of oxygen swapping back and forth.
But this chemistry isn't just some abstract theory happening in a lab. It has massive real-world consequences for us. Oxygen is constantly bombarding everything around us. So how does this invisible oxidation war actually attack our everyday belongings, or even our groceries?
So, the crucial point here is that oxidation is often incredibly destructive. When oxygen and moisture in the air team up to attack metals, we call it corrosion. This is exactly what causes the rusting of iron. It's slowly, continuously eating away at our cars, our bridges, our tools. But oxygen doesn't just eat metal, it eats our food too. When oxygen attacks the fats and oils in our snacks, it causes rancidity. This is exactly what ruins our favorite foods, making old butter smell absolutely terrible and turning your favorite chips completely stale. Have you ever opened a bag of potato chips and felt super annoyed that it was like half full of empty air? Well, such the yehe, that air isn't empty and it definitely isn't oxygen. Manufacturers intentionally flush those chip bags with unreactive nitrogen gas. The nitrogen acts as this invisible shield, physically blocking the greedy oxygen from reacting with the oils in the chips. It completely prevents rancidity. So yeah, that extra puff of nitrogen gas, it's the only thing keeping your snacks crispy and fresh. Which brings us to our final thought for today. Chemistry isn't just happening around you, it is you. During digestion, your body is actively breaking down carbohydrates into glucose. Then, in a process called respiration, your cells combine that glucose with oxygen to produce the energy that is keeping you alive right this very second. It releases energy, making it a classic exothermic reaction. Literally every breath you take, every single move you make, you are a walking, talking chemical reaction. So, I'll leave you with this. Knowing that you are a living, breathing laboratory, what beautiful chemical equations are you writing right now? Thank you so much for exploring the everyday alchemy of our world with me, and hey, keep observing the magic around you.